Good morning, or indeed good afternoon or good evening, dependent on where you're listening from in this world of ours. Welcome to this month's webinar from Sigma-HSE, looking at the topic of Hazard and Operability Studies, or HAZOP, known for short. So your speakers today are myself. I'm Andrew Fowler. I'm the Technical and Operations Director at Sigma-HSE. And you can see from this very short bio, been on this subject of process safety for over 40 years now, but started out in chemical manufacturing and then joined the UK's regulator, the Health and Safety Executive, as a process safety specialist inspector for 17 years, and then the past 15 or so years I've been in process safety consultancy. And my US colleague, Andrew, will introduce himself.
Education in chemical engineering, got my start in industry in LNG production and an African facility. Spent time kicking around with a major EPC there, switched over to process safety role with an LNG handling company in the US. And in the last 6 years or so have moved into a consulting role in process safety, performing HAZOPs, PHAs, audits across a wide variety of industries, including oil, gas, energy, chemical production, aviation, and other ones here and there.
Thank you, Andrew. So what we'll be doing today is just taking you through, what is this process hazard analysis and HAZOP study, the methodology and merits of doing this study, why it should be done, what you need to do to prepare for it, how you actually carry it out, and the conclusion of the HAZOP. What do you get out from it, really? Very important. But just before we start this, I'd like to tell you just a little bit about Sigma-HSE. As you can see from this slide, we're a global company with process safety consultancies in Winchester in the UK, which is where we're headquartered, but also in Londonderry in New Hampshire in the States, and in New Delhi in India. But we also have the luxury of running a couple of laboratories as well, where we can undertake flammability and explosibility testing of gases, vapors, liquids, mists, and powders, and chemical reaction hazards assessments as well. So we have all that capability. So as we say, consultancy, the luxury of testing laboratories, and we also do a fair bit of bespoke training for companies as well on practically all of the subjects of process safety. So this just gives a very short insight as to the sort of work that we do. We spend a lot of our time doing what we call DSEA, dangerous substances and explosive atmosphere regulation assessments, or DHAs in the States, or ATEX assessments in Europe, but can also handle the whole gambit of anything to do with chemical process safety management, whether that's undertaking various forms of risk assessment, HAZID, HAZOP, LOPA, various other ones, consequence modelling, functional safety, and indeed any aspects of the management of process safety, whether that's developing management systems from scratch or developing and implementing workable procedures and policies on a site itself. As I say, we've also got the testing laboratories where we're experts in getting a grip on the fire and explosion properties of powders, gases and vapors. We're also got expertise in electrostatic properties of materials and chemical reaction hazard assessments. So as a way of introduction then to this subject, before I hand over to Andrew, who'll be giving the vast majority of this presentation, I just wanted to introduce the topic of this webinar, HAZOP, which is a hazard identification methodology which was developed back in the 1960s. So, that's a good 50 plus years now where we've been using this technique, and it's still considered one of the primary tools for process safety professionals to have within their tool bag. Okay, because it works. There are, of course, a large range of hazard identification tools out there, some of which are a lot simpler, the use of checklists, what if analyses, hazards and things like that. But it's all what we call in the UK horses for courses. You can indeed use HAZOP as your main hazard identification technique, but as you'll find out from this webinar, it's quite resource intensive. And for simpler hazards, you know, if we're looking at the hazards of transport operations on a facility or whatever, HAZOP would not be your most favoured tool to use. There are other ones there, okay? But it is important because if we look at the UK and Europe, for a long time now, health and safety frameworks have all been based on what's called goal-based, risk-based setting legislations. So they're based around carrying out this subject called a risk assessment. And in fact, every piece of health and safety legislation or regulation in UK or Europe requires employers to undertake a risk assessment. It's the starting point for everything else that the business does with regard into health and safety. And as many of you will know, risk is a function of the consequences of a hazard, the harm that that hazard could do, and the likelihood that that harm will actually be realised. So therefore it goes without saying, really, that identification of a hazard is the key step. If we miss a hazard, if we don't, if we forget there's a hazard present, we won't then consider measures, barriers, safeguards to protect ourselves in our process designs. Now, it sounds a simple subject, and in fact, when we look at the high-end process safety legislation, like COMA in the UK or Seveso in Europe, they set us an impossible task right at the start in those regulations. They tell us to go away and identify all of our major accident hazards, all of them. Now, we're talking about serious hazards here when we're in process safety land. We're talking about hazards which, if they're realised, have the potential to cause numerous fatalities, for example, or serious harm to the environment. Okay? So it's key that we don't forget about a hazard. And it's hard, even at the end of carrying out a good HAZOP study, you can't guarantee that you've identified all the hazards. Okay, but we need to make sure that we do our best. It's a difficult thing to be done. Generally, it can't be done alone. It requires knowledge and expertise of a team to be able to do a HAZOP study correctly, because no one person is likely to have all the knowledge and expertise around a particular process in the detail that's necessary to do this sort of study. And it also requires a robust methodology that drives us not to forget to ask relevant questions, etc. Yeah, we need our brains in gear to be able to do a HAZOP. And that's why when we set foot and start going on to do a HAZOP study, we've got to realise that it can require a lot of resource. The HAZOP technique, the tool, is a very robust methodology, but it requires a team of knowledgeable and competent people using this methodology, which is very structured in its questioning and led by somebody skilled in the art, and then hopefully we'll do a good job. But like everything in life, the outcome from a HAZOP is as good as the effort that we put into it. Yeah. So I'm now going to hand you over to my colleague, Andrew LaFlash, to take you through what you need to do to ensure that your HAZOPs and this required large amount of resources that you're going to use to do the job properly is actually worth it. So I'll hand over to Andrew now.
Thank you. Probably incident anyone that's been in process safety or has touched upon it in the last 20 years is familiar with. The BP America's Texas City refinery explosion was kind of a keystone event in the US development of its process safety requirements and standards. Back in 2005, they were going through a restart of a hydrocarbon isomerization unit. You know, they were working long hours. There was mandatory overtime, short shift. There were other work being done in neighboring units with soft-sided wooden trailers located near this unit. And what happened was there was a failure of a level instrument within a distillation tower. They didn't receive notification that they had overfilled it. And this resulted in flooding of the tower and then forcing these hydrocarbons out of a vent stack, as shown in the Chemical Safety Board picture on the left side, and shooting fireballs into the area, which resulted in the demolition of those trailers, damage to the unit, and unfortunately 15 deaths and 180 injuries. There were numerous things that contributed: overtime, lack of management of change, but they also found during the investigation that the PHAs that were performed for this process were kind of just there to check the box. They didn't really look at what the consequences of overfilling the tower were. They didn't look at all the potential causes of a high pressure scenario. And they didn't really understand the safeguards that they applied to their scenarios. They just said, yes, we have it, and it's good. And then you also find there had been 3 previous incidents in that same unit that weren't addressed in any of the revalidation PHAs that were performed for the unit. So there are items, if they had taken the time, identified, worked through the causes and what safeguards they could in place to prevent these near miss incidents, they very likely could have avoided this catastrophic incident as well. And we're going to look at, how you can do a good HAZOP to try and make sure you do check all your boxes, look at all your causes and your consequences using the HAZOP methodology. Okay, Andy? All right, so first we'll go over some basic terminology and the kind of the guidelines for the study before we dive into anything too in-depth. All right, so your hazard, inherent physical or chemical characteristic that has the potential for causing harm to people, property, or the environment. So you're looking at if it's a flammable, if it were to be released, is there a potential for a flash fire, an explosion, a deflagration? Is it toxic? Is it dangerous to the environment? If you were to have runoff into an adjacent waterway, are you looking at a fish kill? Or if it's something really bad, are you looking at, say, a permanent Superfund site type of thing? And ranking, what type of hazard each material in your process has, and then the realisticness of that. Process hazards are, you're operating within an envelope. You have set pressures, set levels, set temperatures. If you were to have a wild swing and you were to lose temperature control on your process, could that lead to an ignition event or a runaway reaction if you've got a reactor and you lose process cooling? These hazards are typical to how you're running your process and not specific on the material as such. And then there's non-process hazards, which we're not as concerned about in the PHA, are generally handled through your job site analysis and your field safety. That's, do you have fall from height concerns? Is there potentials for slips, trips, and falls? Improper PPE being used for the tools. That falls kind of outside the realm of the PHA and the HAZOP methodology, but you still want to make sure you're capturing them using the correct tools and methods. All right, so process parameters, you look at your different parameters within the study. So if you've got a reactor vessel, you're looking at pressure concerns, temperature concerns, level concerns. reaction speed concerns. And then you're looking at the design intent. You know, what is that unit supposed to be doing? Is it a heat exchanger? Is it just simply a transfer pipe? Is it a storage vessel? Is it a reactor? Is it a vent stack? What is the intent of design here, and what happens if it isn't? And your deviation covers that. So you're varying from what it's designed for. Loss of your heat exchanger, you don't heat the fluid to a desired temperature, you don't receive the cooling you want. You lose your gas flow on your distillation column. All right, now you have all your liquids dropping out and you're not getting a good distillation. Could there be a potential for materials to make their way into a process stream they're not supposed to if you were to drop this? So what can change within your process that could then lead to you having a concern that you need to explore within the HAZOP and PHA? Okay. All right, your process risk. So that's your risks associated with the process hazards and its consequences. So it's a high level leading to an overflow. If it's, you know, a rain containment facility, you've got, you know, it's just drainage on the side of the road, your sump pump fails, you have an overflow there. All right, your road might wash out. But if it's a chemical containment bund around storage tanks and you have an overflow there, now you're looking at, all right, is there the possibility of personnel exposure from this? If it's a flammable material, could we now have a pool fire because we have this flammable material sitting there? So you look at what your process hazard is, what its consequence, and that'll give you your risk. So PHA is your overall technique for identifying and analyzing the significance of these hazards. A HAZOP is one of those techniques you can use. You could also use a bow tie. You could use a HAZID, what ifs, checklists. In the US, there's no set requirement for a methodology. It's whatever works best for your process. And in most cases, that's going to be your hazard and operability study. And then process information, physical, chemical, toxicological information related to your chemicals, process, and equipment, P&IDs, process flow diagrams, energy balances, your equipment information, you know, what is its max allowable working pressure? All that falls into your process information. All right. So within your PHA, you're looking at identifying any potential causes, consequences, the mitigation and prevention of fires, explosions, releases of toxic or flammable chemicals, any major spills of hazardous chemicals. And really we're focused on the equipment, the instrumentation, utilities, human actions, and external factors that may impact the process. You know, do you have well-written procedures? Is your process designed in such a way to prevent human failure when needed? And the different methods, HAZAD, HAZOP, what if, checklists, FMEAs, and bow ties are generally the most common. Okay. So your HAZOP and operability study is really the most structured method for the PHA. You know, you're looking at it on a piece of equipment by piece of equipment basis, each parameter for that designed intent equipment and how it can fail. And that gives you kind of your most comprehensive understanding of what you have, what your issues may be, and it's all based on your guide words. And you want to have, like Andy was saying, a multidisciplinary team. You don't have a single individual, you have a facilitator, you have design engineering, test engineering, safety, maintenance, operations, as many groups involved with the process as possible to make sure you're getting that high level view. Okay. All right, so why do a HAZOP? In the US, if you're handling over 10,000 pounds of flammables, or if you have a material listed in Appendix A of OSHA 1910.119, over the quantity threshold limit, you're required to have a PHA, and a HAZOP's a good method. Even if you have a process where you're slightly concerned, you know, it's a new process to your facility or you're dealing with a chemical that you're not used to, It can help you design the process in such a way that it's inherently safe. You can use it as a procedural development tool, making sure that your procedures are written in such a way as to avoid human failure opportunities. You can use it as a systematic check of your safety and operability. Do the safeguards you have in place make sense for what scenarios may actually occur? Are you over-instrumented, leading to false trips and operability concerns, or are you under-instrumented and there's the potential for you not to detect failures until it leads to a catastrophic event? You know, you can use it as proof of performing your due diligence to attempt to identify and address as many hazards as possible. And it's an acceptable form of PHA. It also allows confirmation that process modifications aren't introducing new hazard scenarios when you do have a change within your design process, either new equipment, new materials, or new procedures. Okay. So like I said, it's a team activity. You want to identify as many possible causes that could lead to a hazard as you can, as well as the possible consequences identified with those causes, and to ensure that you're making a qualitative judgment of those risks. And it is an iterative process. So if it is a OSHA PSM covered process, you're required to revalidate every 5 years. So as your process matures, you develop a more complete understanding of what hazards exist within that process. Okay. All right. So multiple points when you can conduct a HAZOP. During the feed, you know, you're getting your feet wet, you're deciding what design you want to go with. You can perform a HAZOP and kind of rank the different potential technologies against each other to determine, you know, if one has more risk than another, if there's potential more hazards in operation. Once you've reached a detailed design point, you know, your sanity check that your safeguards in place are effective and address the concerns that you've identified. Anytime you're making design change, once you've finalized a design, if you have a management of change process, if you're making anything greater than a like for like, you should at least look at it and see if there's new risks. And if it's a major change, you may want to update your HAZOP there. Pre-commissioning activities, you know, construction's completed, you're about to start up, perform a HAZOP on your commissioning activities to make sure your commissioning procedures make sense. Normal operation, audit requirement, periodic study is required by governing standards, 5-year revalidation if it's OSHA PSM covered. If a facility has an incident, there may be a directive that they update their HAZOP at a greater frequency than 5 years. All right. So part 2, HAZOP study. This will be the meat of the study. All right. So you're identifying your potential hazardous scenarios, your potential deviations from the design intent and operability issues, identification of further preventative mitigative actions where calculated risk associated is higher than the acceptable level, identification of scenarios requiring a more granular analysis than HAZOP provides. Sometimes you'll have scenarios where, you know, it's a high risk, high likelihood, and HAZOP flags it, but you want to have a more granular approach. That's where company or corporate procedure may dictate, all right, this scenario is singled out for a LOPA, and you would then perform a layer of protection analysis in addition to your HAZOP for those scenarios. Prior to performing the HAZOP, you need your process safety information, which would be your process flow diagrams, PNIDs, layouts, plot plans, SDSs for any of the chemicals involved in the process, or if you have storage in the near vicinity with a potential domino effect, you want to make sure you know what would happen if you were to impact those storage. Process description, operation sequence details, be it, you know, if it's an automated process, what does the process entail? If it's operator driven, what are their procedures that they're following? Your heat and material balances, equipment data sheets, any procedures involved in operation and maintenance, startup and emergency procedures, and cause and effect diagrams for any of the automated safeguards that you have in place. So once you have all that information, you can do the prep work, which is generally the facilitator setting. He'll identify the different nodes or sections of the process that would fall under one design intent, look at those to determine which parameters are involved within that node, and then he'll prep that document so it's ready to go when you have your HAZOP sessions. To have your HAZOP sessions, that's sitting with the team, working through what could go wrong, what do we have in place, what would the consequence of this be, what safeguards do we have, do we think we need more safeguards? And then after you complete those sessions, a report is generated that identifies any open action items or opportunities for improvement, and that's given to the team to go ahead and follow through to close out. All right. So yeah, the review of the PSI, node definition and markup, terms of reference for the HAZOP study. If it's a new team kind of not familiar with the process, you want to make sure everyone involved has a basic understanding, not only of what you're doing, but the terminology and the kind of the guideposts to make sure you're getting the most value out of your study. So a node can be system-based, process-based, depends on the operation. Usually it's process, design intent based. So if you have something simple like LNG peak shaving facility, you'd have, truck transfer from the truck to a bunkering tank. So from the truck to the tank would be one node. The tank itself is designed for storage. So that would be a different node with its PSVs and instrumentation involved. And then for sending into the supply system, you'd have the outlet pumps through vaporizers to compressors to your supply piping to utility users. And each of those sections would be its own node, and you'd look at the different parameters for each of those nodes. Okay. So within each P&ID, it would be marked up. You would go ahead and highlight, this is node 1, this is node 2, this is node 3. So everyone looking at it can see what is actually part of that node, and it helps you understand, all right, so from this green line to these green lines is one node, and then here to here is another node. So you're only paying attention to initiating events that fall within that node. Consequences may fall outside of the node, but your initiating event has to occur within that blocking. And then every HAZOP will have a risk matrix. There's a variety of different risk matrices. This is just kind of a standard industry one I'd use. Likelihood going from once a year to once every 10,000 years, and then severity depending on impact. So if you're looking at impact to plant personnel, anything from a minor worker injury, which would be a first aid, up to a potential fatality, and that would give you your range of consequences. Obviously, a low consequence is allowed to have a higher likelihood and be considered acceptable, whereas a higher consequence requires a lower likelihood, with the worst being, a fatality can only occur once every 10,000 years to be within what's normally considered industry standard for acceptability. All right, so deviation is a combination of your parameter and a guide word. So for flow, it's a pretty common parameter. You'll have, what happens if you have a high flow scenario? You're supposed to be sending 3 gallons per minute of this chemical into the process. You were to change out a pump, and all of a sudden you're pumping out 15 gallons per minute. Less flow if you were to have an obstruction in your line, and now instead of sending that 3 gallons, you're sending 1 gallon. No flow if a valve were to fail closed or a pump were to be shut off and you no longer have a flow. What could happen there? Reverse, you install a pump backwards, or you have a pressure differential you weren't expecting, and your flow path is now the reverse of what you're desired. Or maybe it's misdirected. You have a supply pump that supplies an A and a B tank. Someone opens the wrong valve. You think you're filling tank A, you're actually sending to tank B. What could a consequence of that be? And that would be your deviation that you're looking at. Okay. All right. So safeguard types, there's 3 types of safeguards. Prevention being the most preferred. It prevents or reduces the likelihood of an event. That would be level controls. You've got a high level alarm on your storage tank. It goes off and it shuts off your incoming feed. You've got gas detection in the area at 25% LEL. It alarms and alerts operators to know, there's an issue here, there's a leak, something needs to be done to address this. Detection, indication, something's already in progress, but you can detect and respond that way. Fire detection, if you've got pressure indication in a vessel that's not supposed to see pressure, maybe a vent stack, and then your mitigation, which least effective, last ditch usually for your safeguards, and it reduces your severity. So you're looking at, you have a foam suppression system to reduce fire, you have a snuff, you have an emergency response that triggers a general evacuation of the area. Something that it's not going to prevent the event, but it does lower the consequence from its operation. All right. So most people are usually familiar with the safety onion. The closer to the center, the more effective it is, starting with an inherently safe design. For this, the safest plant is a plant where, it's designed to operate with all of, you can't overfill it, you can't overpressurize it. Not always common, can be expensive. That's why we go to, all right, basic process controls are your next step. That's how you keep your process within its desired set points. You control flows, levels, temperatures. After that, you have your non-safety process alarms. You start to creep out of your desired operating envelope. Operators receive an alert, hey, you're 5 degrees above where you want to be on this. What are you going to do to correct it and bring it back to acceptable? Then you have your SIS, your safety instrumented systems. That's your automatic action. It's detected something and it's going to respond. It's either going to vent, shut down your process, something outside of normal controls and alerts to render your process into a safe condition. And you have mechanical protective systems. If you've got diking or bunding around an area, you've got your pressure relief valves, something that physically acts to prevent spread of a hazard. And then finally, last ditch is your incident and emergency management procedures, your evacuations, firefighting, all of your kind of last ditch, something's happened, but you're going to lower the impact of it. Okay? All right. So team composition of your HAZOP. Team composition is really important. You want to make sure you have the knowledge in the room that's going to make your study successful. Always need a facilitator trained and experienced in the method being used. If it's a large enough study, you've got a large thing you're going through, usually you'll have a scribe as well. So you have the facilitator leading and directing the discussion, and the scribe will be recording within the software. If it's a smaller, less complex process, a lot of times the facilitator will scribe as well. You've got process engineering in the room, design engineering, controls, ops, maintenance, safety engineering. And then you may also, depending on the process, want someone from logistics there. You have this material showing up to site. Is it in 55-gallon drums? Is it in totes? Is it, bulk tank unloading? How is this material making it to site? You may need someone from logistics for that. Commissioning engineering, if you're going through a startup of a new unit, you want to make sure you have someone from commissioning there so they can walk through their commissioning process and correct you if you have any misunderstandings on what they'll be doing to get that unit up and running. vendor package specialist, if you're getting a skidded system for air compression or nitrogen generation, and you're kind of factoring that into your overall plant design, you want a representative from that manufacturer to be able to talk to the safeguards and the features built into the equipment that they're selling you as turnkey. And then electrical engineering, if you have questions about wiring or area classification, you want to make sure you have someone with the electrical engineering background to answer those questions. All right. So roles and responsibilities. HAZOP facilitator, he'll define your scope that you're analyzing. Where does the process start? Where does it end? And within that scope, he'll go and he'll define your nodes. And he'll lead the session. He'll talk about, what guide words we're using, what parameters. Direct the flow to kind of keep the meeting moving and to keep the conversation relevant. A lot of times you'll run into potential for people to try and solve design problems within the HAZOP session. And he'll have to step up and kind of either table it or put it in an action item to chase something and drive that meeting towards relevant conclusions and the generation of practical recommendations, keeping kind of the large scale stuff to the side and making sure you're getting the most out of your time spent on the study. They should be independent from the design team, either a third-party company, or if it's a larger company, it could be somebody from a different division. The worst thing you can do is have an engineer critique his own design. It's going to be a lot harder for him to identify issues if they're his issues and be kind of non-committal and not driven to want to be able to say everything's good if it's, his hands have been on it. Okay. The scribe, he'll support the facilitator. He can assist with node definitions and drawing markups, record the proceedings within the worksheet, be it Excel, PHA Pro, PHA Works, whatever software package is being used to perform the study. They also, if you do have a scribe, generally perform the first draft of the report for review and approval by the facilitator. And then each of the HAZOP participants kind of has their own role to play within it. Process engineers there to talk about the process information. Operations experts are there. What's the philosophy of operation? What methods are used? Project engineer, details and procedures for the implementation of that specific project. And then other members, what is their cornerstone of expertise? If they're maintenance, is there a method that they're performing tube bundle maintenance on where, it's not designed for, but it's been common practice now, you drop, say, a tube bundle head without flushing the system? Do we need to call out that, it requires a purge procedure first? What are they doing that may have a risk that the design engineers wouldn't be able to identify? And how can we address those needs? Okay. All right. So the procedure, reiterative. You start with selecting a node, a parameter, which would be your pressure, temperature, level, a guide word within that, more, less, no, reverse. Develop potential deviations within it. Can you overflow? Can you overpressure? Can you send stuff somewhere you don't want to? What potential causes of that exist? Could a valve be shut due to operator error? Could there be a failure of an instrument resulting in your automatic controls misbehaving? Record what the significant consequences of that could be, and then as a team estimate the severity, likelihood, and risk of that scenario. And then looking at that risk, do you have any recommendations required to reduce that risk to an acceptable level? And if you do, document those recommendations. If not, you're safe, you move on. Are there any other potential deviations for that guide word? If not, are there any other guide words for that parameter? If you're finished with guide words for that parameter, are there other parameters for that node? And then within that, you're good. Are there other nodes within the study? And you just keep looping through this process from the start of the scope through to the end At the end, you'll have your first study and then something for you to build off of as you move forward on your future PHA revalidations. All right, so the sessions themselves. All right, this is just an example of what a HAZOP worksheet would look like in Excel. It's got all your project equipment, drawing information at the top to identify where this is coming from. It's talking about your guide word and your parameter. So this would be a more flow, the cause, a flow transmitter malfunctioning for raw material A. Potential consequence would be, accumulation of material A within the process, maybe a runaway reaction, could be a reactor rupture because of the high pressure and injuries and fatalities on the shop floor. Severity of 4, which would be your potential fatality. Likelihood of 3, instrument failure is generally a 1 in 10-year event, which is where the 3 comes from. A risk of B, which as you can see is orange, which would be in this risk matrix an unacceptable risk. And then you look at, okay, what safeguards do you have in place already to reduce this risk? So there's a temperature element that will alarm on high temperature and dictate an operator action. There's an interlock on a feed XV that will cut off feed to the reactor. And there's a pressure transmitter on the reactor that also cuts off feed to the reactor at high pressure. Taking into account the independence of the safeguards, you drop your likelihood by a factor of 10. It's still a risk of C, which is 1 above your acceptable risk level per the matrix we looked at earlier. So recommendation is to implement a PSV on the reactor sized for worst case scenario. So if there is a pressure buildup, you'll relieve out this PSV, which is routed to a safe location, rather than a rupture of the vessel causing fatality of personnel. And you would do this for each node, each guide word, each parameter, and as many causes and consequences as you could. And if it comes back as, the inherent risk is safe with the safeguards you have in place, then you're okay and you don't require any additional recommendations. But if, like these scenarios, you still have a risk above acceptable, you're required to implement recommendations to be followed up with after the completion of the study. Okay. So after the workshop, it starts with the report preparation by the facilitator and the scribe. Then the project team has an action tracking register. It could be however they track open action items on the site. It could be a master list. It could be EH&S software. However you need to make sure you're tracking not only that we have these actions, the steps taken, how we're closing them, and once it's closed, proof of closure. And then you have your HAZOP closeout report, which would show, yes, these have all been closed. Okay. All right. So typical contents in your HAZOP report: introduction, a brief description of the process and the facility, a list of the process information that was referred and used. That way, as you go through, you know that for the study in 2015, you had PNIDs 1 through 10, revision 4, but now it's time for your new study and you're up to revision 8. You want to make sure you're identifying any potential changes to your HAZOP that would come from the changes on those drawings. Description of the methodology used, the composition of the team, including roles and levels of expertise for each member, any of the recommendations that resulted from the HAZOP study, and then appendices, including the marked up PNIDs and the HAZOP worksheets from whatever software package was used. All right, so key success factors. You want to make sure the drawings and the data used for the study are accurate. If you know for a fact the PNIDs you have don't reflect your in-field conditions, it's important to redline those PNIDs prior to the study so you know you're actually looking at your in-field conditions. Experience and skills of a HAZOP facilitator. You want to make sure you have someone that's familiar with the process, as well as has experience either leading or scribing and is now being the lead with an experienced scribe, someone that has the ability to direct the study and ensure you're getting valuable communication out of it. Technical skills and insights of the team. If you have a brand new operator that just started a week ago, they're not going to be able to give you as much insight into the process as someone that's been working the process for an extended period of time. Duration available for preparation of the HAZOP sessions. You want to make sure you give adequate time for the nodes to be developed and the PSI to be reviewed prior to walking through your HAZOP. Schedule of the sessions. Scheduling is kind of some people only have, they do half days, so you'll do 5 4-hour sessions, which is fine, or you can do 6-hour sessions. I've seen people try and do 16-hour sessions, and that just, you don't get effective results if you're forcing someone to sit and walk through this process for extended hours each day. It's important that you think about team involvement as well as your deadlines. And then, you know, ability of the team to use HAZOP approach as an aid to identify deviations, causes, and consequences. You don't want it to come across as you're accusing anyone of not addressing safety concerns or doing things the wrong way. You want to make sure that you're explaining operator error doesn't mean, you know, it's the operator's fault. It's more the systems in place have left this opportunity for human failure in place, and how can we address that to assist people in not being able to have an issue. And you want to make sure you're maintaining a sense of proportion, especially when assessing the severity of your potential consequences. You don't want to end up on the side where, you know, you have the potential for a vessel rupture at more than 3 times the max allowable working pressure, but the team's trying to say it would only result in a first aid. And you also don't want to end up on the other side where, you know, you may have a leak on a water system and you're saying, you know, there's a potential fatality, if really it's just, you know, you might have some environmental impact from dirty water making its way to runoff. You want to make sure you're keeping your eyes on the goalpost and you're kind of keeping it centered and realistic. Okay, so your advantages, it's systematic. You know, it's not some of the other methods kind of jump around or require you to have a very thorough understanding of what has occurred in the process before. Whereas your HAZOP, you look at your drawings and you go step by step through your process and you're looking at it. It's a multidisciplinary study. You know, you get input from people from all walks within the process. It's not just operations doing it, or it's not just design engineering or maintenance. It's everyone coming together and comparing their experience with the process to get the best realistic picture of what you have. You're utilizing that experience that people have with the system, and it covers your safety and operability aspects. So you're not just looking at could this cause an injury, but no, what would happen if we close this valve and we were to, you know, it causes material to freeze in the line and now you have a clean out of 4 days. Is that, it doesn't hurt anyone, which is good, but now you're looking at a loss of production, which is a loss of income. Is that a concern that you want to address as well? You want to make sure you can use it for your human factor analysis and assessment. So you can run procedures through the HAZOP process in addition to your P&IDs, and you look at it on a step-by-step basis for what would happen if someone were to perform this step in the wrong order. What were to, if you perform the step on valve A instead of valve B? You know, is there too much information in this one step where you're requiring an operator to go from point A to point B to point C, and they're running all over the facility, rather than logical, you go A to D, which is right next to each other, to C to F, and it's just a straight linear progression. So part of it is suggesting solutions for your identified problems. You don't only identify that there is an issue here that needs to be addressed, you use that team knowledge to come up with what is a potential solution for this, and then it can be explored in greater detail later to make sure that that solution does make sense. And then your proceedings are recorded and always available for reference and training purposes, and you have something to work with the next time you need to review. It's not a fresh slate every time, it's iterative. So there is some differences between batch and continuous processes. So with batches, you're looking at, quantities of addition. Continuous, it's a flow rate. Likelihood of contamination differs between the two as well. With batch, it's higher because, there's multiple, you stop, you start, you stop, you start, you're manually adding stuff. Continuous, it's usually dosing, and it's from, from bulk storage or totes. Automation, batch process, it's most likely going to be a manual operation, whereas continuous processes, very rarely is it more manual than automated. And set points, depending on your batch process, you could have multiple set points for a single vessel as you step through a process, whereas continuous process, normally your set points for a piece of equipment remain not static, but within the same range as it progresses. And then, of course, higher dependence on human operators and lower dependence for continuous process, which is just something to take account or when you're doing your HAZOPs. All right. Andy, I'll turn it back over to you.
Yeah, so thanks for that, Andrew. Thank you very much. I hope everybody found that interesting and useful. Needless to say, Sigma-HSE has got a team of HAZOP and other risk assessment facilitators. And in fact, one member of my team literally spends his whole life going from one HAZOP to another on different processes. We've been so busy with them recently for the past couple of years. So it's good to see that the technique is still flourishing and still being used widely throughout lots of processing industry. So thank you very much for attending and listening. Because you've all registered, you will be given a link which will take you to a recording of this webinar, so you'll be able to see the slides again and listen to myself and Andrew fluent talking. But if you want to contact us, if you want any help on deciding what technique to use or anything else, give us a call or send an email to info@sigma-hse.com and we'll get back to you and we'll help you in any which way that we can. So I hope you've enjoyed it. I hope you found it enjoyable, and I'll say goodbye to you at this point. Thank you very much.